This is the Decision 1 exam from 2021. Let's just go straight into it then. So we've got a Hamiltonian cycle, which is just a cycle that goes through every vertex once and returns and ends where it started. So we start C, then V. You can cross them out as you do them, then E, then X, then A, then W. From W, the only place we can go to that we haven't been to yet is D, so that'll be the next one. Then it seems very logical to go to Y, and then we can go to B, and then we can go to U, and then we can go to A. Now, if we're doing the planarity algorithm, the best thing to do would be to redraw this using that cycle we just found, so C to V to X and so on. So I've drawn this shape out here that just goes round in that cycle. Now I'm missing a bunch of edges. So now we just look back in here, and you can maybe start at C if you want to, and say, okay, well I've got the edge from C to U and the C to V. I've already drawn those in here and here. But I also need an edge from C to W and from C to X. So I'll put those edges in, and then I'll look at V, and I'll be like, okay, V, I've already got C and E, but it still goes to A, and it still goes to, where else does it go? I've already said C, also goes to B, it looks like, so I'll put those two edges in, and so on as I go around. I'll just do all of that, so I'll add on the edges that we haven't got. And then to decide whether this is planar, we just need to write down all the edges that are inside this shape, and then just pick one to say we'll keep that in the inside. So I just picked C to X. I said I'll keep that one on the inside. Anything that it crosses, which is V to B, V to A, and E to Y, all of those will now need to be moved to the outside. But there's a problem here because now we can pick this one, V to A, and we can say anything V to A crosses, that needs to be on the inside. Now that's fine for C to X, because I already said that's on the inside, but E to Y therefore needs to be on the inside because it crosses V to A, which I know needs to be on the outside. But I've already said that needs to be on the outside too. So we have this problem here, which they'll intersect no matter what I do. So it's definitely not going to be planar. I should probably have written down somewhere. Oh, sorry, I have written down is not planar. Good. Excellent. Number 2 then, we'll be doing, I can't even remember what this topic is called because I can't remember anything. But what we need to do is we first need to work from the start here. So we'll obviously say 0 and 0 here, I guess. And just go out this way, and we'll do these top boxes with the maximal time that it takes to get there via any route. So here to get here clearly is 4, just there's only one route, and then here is 6, and then here is 10, that's fine. But sorry, immediately wrong already, because you could say this is 6, of course, couldn't you? But I just said we need the maximal time. 4 plus 4 is the maximal time, and that gets us to 8. And likewise here, 6 plus 5 is bigger than 10, so we'll use an 11 there. Except we won't, we'll use a 13, because apparently we can do, of course, 4 plus 4 plus 5. So you just have to be much more careful than I'm apparently being in this voiceover to actually look for all of the roots before you do this. Now D, likewise, you could just be lazy and say 4 plus 2 is 6, or you could say 4 plus 4 is 8, and then this doesn't take any time, so we're actually going to get to 8 up there. And then likewise here, what's the maximal time to get here? Well, it's either 8 plus 6 or 8 plus 7, which is of course maximal is 8 plus 7. Here is just going to be 8 plus 2 or 13 plus 0, which is the maximal being 13. I'm obviously being much more careful now because I don't want to embarrass myself further. Is this going to be either 15 plus 7 or 13 plus 6, or 15 plus 7 is bigger? And all the way down here we've got 13 plus 5 is the only way to get there, which is 18, and then of course 18 is... I should have filled this one in last, because if this one was bigger, that would have been there as well, but it doesn't really matter. And we kind of knew that this was going to be that. Anyway, from here you work backwards, and this time you choose the smallest thing you can every single time. So start with 22, and then to get to here, well, that costs nothing, so that will just be 22. And then to get to here, we just take away 5, so that's, it would be 17, but the minimal is 22 to take away 7, which is 15. So again, we're looking for the minimal thing here. There's only one way to get here, so this is just going to be 22 minus 6, which is 16. And again, only one way to get here anyway, so that's going to be 22 minus 17 is 15 as well. And then, okay, again, minimal to get to here, is it going to be through backwards through here? Well, that's actually the only way to do it, so we'll do that. And then backwards through here as well. Or, I guess you could go backwards through here. But 15 take away 7 is 8, which is minimal. And then keep going backwards here, so backwards through 4. 8 take 4 would give us 4, 9 take 2 gives us 7, so we'll go for a 4 here. And I think that's the whole thing filled out. Each activity requires one worker, and products finished in the shortest possible time, obviously. Calculate the lower bound. Well, you just have to add up how long all the jobs are, so 4 plus 6 plus 4 plus 2 plus 10 plus 5, and so on, you get 71. Usually it just gives you that information, but you just have to sit there and type it into a calculator. It takes 22 days or whatever. Is this in hours or days? In hours, apparently. So we just have to do 71 divided by 22. to find 3.2 rounded up to say that 4 workers will be required. Fill in the grid. So here's a grid here. So I've just got rid of this because it's not very helpful. I'm using this here and the grid here. So A, B, and C can all be started at the start. So we may as well just use 3 workers to, or just do A, B, and C from the get-go. Worker who's doing task A will finish first. So he may as well start. He can start on D or E. But I decided to start on E since this is the critical path here. So it seems logical to try and get that done first, at least for now. Likewise, B finishes. So we could put him on D real quick because you can't do H or I until task E is finished, right? Because that follows on from them. So the only task he can actually do, he could do task number F, I guess. No, he can't because that also requires on E to be finished as well. So the only task for him to do is D. And then he finishes, these two both finish at the same time. G is unlocked now. We could do task G, and we could also do task H, I, or F since E is now complete as well. So we'll just put him on H, the first worker on H, why not? And we could put the second worker on G. Again, trying to follow this critical path, I guess, is important to try and get that done early. Worker C finally finishes. We may as well complete up objective F now, so that we can unlock some of these tasks over here. I still needs doing if we're going to try and get K done eventually. So when this guy finishes G, he may as well do I. And then we've just got J, K, L, and M to do. I think we can do them all once H and F are done. So we'll just slam them in somewhere. It's not really going to make a difference. We can just put those all in these places when they finish. The only one that we haven't done is K. Sorry, we have done K. Which one haven't we done? Where is it? L? That one there, L. Yeah, so we could do L as soon as F was finished. So we may as well set worker 4 on L. We have to finish by the 22-day mark, which means worker 3 clearly doesn't have time to do it, so we just give it to worker 4. And that gives us 4 workers to do it, and I think that's probably decently scheduled, I guess. 3 is a shortest distance thing using Prim's algorithm. That's the one where you have to stay only on vertices that you've currently sort of used. So if you start at A, you can only use these numbers first. We're going to go for the smallest, obviously. So we'll pick A to, what's the smallest one here? A to H first, I guess, is the smallest. So now we can pick any of the distances from A or H. Of course, we can't just go back to A, that would be pointless. It's the smallest that doesn't involve A either. I think the smallest one there that's left is A to B, it's 24, so now we can use A, B, or H, of course not wanting to go back to one that we've already used. I think the smallest number I can see left still is probably 27, H to D. So now we can use D as well, and that's a very small number there, so we'll go D to C now. We haven't been back to C yet, so that's fine. So now we can use A, B, C, D, or H. It might be easier to start thinking of it backwards at some point. I can see a small one here is 26. Is that the smallest one you can see? Probably, so it's probably C to E next is 26. Now we can use E as well. The only ones we haven't used are actually A, B, C, D, E, F, and G, I think the only ones we haven't got. So we may as well just concentrate on F and G column and just go, okay, without going from F to G, because that's the only thing we're not allowed to do. What's the smallest here? Well, it looks like this one, so D to G will probably be the next one. And then finally, how do we get to F in the smallest possible way? Well, that looks like F to E, it looks like, and that will be the last one that we have here. And then state the minimum of this spanning tree. Just look up each of these numbers that you found and add them all together, and you get your answer. Next, we have an extra town called J, which has these distances. And it wants us to use the nearest neighbor algorithm to find a route, starting at J, going around all the other ones, and finishing at J. So we start at J, the shortest distance is to F, so we'll go to F. Then it's nearest neighbor, right? So you go to F, and you think, what's the shortest distance to anywhere from F that is obviously not one you've already been to? And the shortest distance here, I think, is to E, so we'll go to E next. Then we're at E. Shortest distance looks like it's C, so we'll go to C. Now we're at C, shortest distance here, and again we can't go back to the ones we've already got, but D looks like a good one to go to. Then we go to D, and we just continue, we look for all of them. And just remember, you do need to go back to J to finish. No matter how long that is, you do just need to go back to J to finish. And then, so that's the route, and then its length. Again, just look up all the numbers you just looked up. You can write them down as you're doing it, it's probably the quickest way of doing it. And you eventually end up with the answer. By deleting J and all its edges, find a lower bound for the length. Well, we already have a minimum spanning tree, so that's really helpful. So all we have to do is use that minimum spanning tree, and then add in the 2 shortest ways to get to J, which are B and F. So take 183, add in B, add in F, and that will be a lower bound. It's not guaranteed that we can do that, of course, although it will work, but that will be the lower bound. Good. Next is this is the Floyd's algorithm question, which is pretty cool. So we've got, I'll just put dashes in here because we obviously not interested in A to A or B to B and so on. Let's just fill this in. So A to B is 57, A to C is 95, A to D is 150. I mean, just look at the table, just read it. B, there's some interesting stuff with B though, because B doesn't go to every other town, city, or whatever this is. It doesn't go to D. If something doesn't go somewhere, you just put an infinite symbol to just say that you can't get there in one go. And then yeah, just fill this in. Use the infinite series symbols if you can't get there all in one go. And A and C are the only ones that are connected to all of the others, and we get this. And now what Floyd's algorithm says is, let's just concentrate on town A first. And what we'll do, so I'll just fill this in. I've just copied this because it's easier for me in PowerPoint to do that. I'll explain what I'm doing in a second. What's it easiest to do? We'll start at A. We'll keep all of A's the same. And now one by one, we're going to look at B, C, D, E, and F. And we're going to go, okay, currently we can get from B to C in 72. But what if we went via A? Would that be faster? So if we went via A, we'd go 57 back to A, and then we'd go 95 to C. Now that's longer than 72, so we'll keep the 72. Now what about getting to D? Now currently we can't go B to D, so going via A, 57 plus 150, is going to be faster, because it's faster than something that we couldn't do previously. So we'll fill that in, and then we'll update this table to say B to D was via A, so we'll put in an A there. Then to E, so it's currently 132, B to A is 57, plus 63 I think is less than 132, so we'll go via A there as well. And then F, well this is definitely going to work because we can go B to A, then A to F. 57 plus 230 is less than infinity, so we'll replace that with an A as well. And then of course all of these ones are just mirrored with these, so I'll just fill those in as well and replace all those with A's as well. Now we do the same from C. So C to D is currently 289, but let's see, can we make that faster if we go via A? So via A it's 95 plus 150, which is what, 245, which is less than 289, so that's good. We can replace that via A as well. And then C to E, so C to E is currently 160. If we go via A, it'll be 95 plus 63, which sounds less than 160. It is just about 158. Go via A there as well. And then C to F is 125. If we go via A, it'll be 95 plus 230, which is definitely bigger than 125. So we'll just keep 125, keep that the same, and then mirror these. And then I won't go into too much detail. Do the same thing for D and E. You don't have to do anything for F because you'll have checked those through doing all the other ones. And you eventually fill in this table here. And you have your first iteration. Of course, what you would then do is you'd play the same trick with the B's, so you'd keep the B's all the same, and then you check every other town via B, and then you do it via C and via D and via E and via F. And eventually, if you do that, you'll get this table here, which is what they've said they've already done. And now we need to find a different algorithm to find the roads that will need to be traversed twice if we want to find a route that goes through every road at least once. Now the thing that's going on here is that every single city has an odd degree, like this has 3 edges, this has 5, 3, 5, 3, 5. We need to start at B and finish E. Now if you have an odd number of edges, what that means is to traverse every road, like imagine getting through these roads to A, you'd go here, here, you could then come back through this one and leave this one, but then you'd have to go back to A via this one because you have to use this road, but then you'd have to use it again to leave, or you'd use one of the other ones again to leave. So if you have an odd number of vertices and you're not starting or finishing there, you're going to have to use one of those vertices twice. Now all of them have an odd number of vertices, so we're going to start on B and finish at E, so we're going to naturally use those. Like if we're starting at B, we can leave via this road, and then at some point later come in and leave again via this road, and we don't have to use any of them twice. But we will have to use one of the vertices at A, F, and all the other ones twice. So we have to consider pairings of A, C, D, and F. So you can do A and C, so you could use the road from A and C twice, along with the road from D to F twice. That could be one pairing. Now there isn't a road from D to F, I'll get to that in a second. But we could consider that pairing, and we just look in the table for this. So A to C, we can just look in the table as 95, D to F, we can look as 275. Now I know there's no road from D to F, I'll talk about that in a second. Or we could pair up A and D and C and F, and that's lesser. Or we could pair up A and F and C and D, and that's a bit bigger. So this is the kind of pairing that we're going to want to use twice, because it's the minimal one. Now the thing is, you can't actually go from C to, is it from C to F you can't actually do? And you can do C to F, and you can also do A to D. But the issue is, you don't actually do A to D. A to D is 150, but we've got 147. So what you actually do is you use A to E and then E to D twice, each. You go here and then here rather than this because it's slightly quicker. So you use each of these roads twice rather than this one. So you actually repeat these 3 roads. C to F is 125, and that's actually just going C to F. So we just use that road twice. And then we just have to do the minimum, the weight of the network, this, because we'll use all of the roads once, except for these 3, which we'll use twice. So we just do this plus this number here, which represents these 3, and we get this number here. And yeah, that's right down the length of the route. Yeah, that's done then. Good. The list of 10 numbers above, I mean to the right here, because it just gives me some space, is sorted into descending order. Use quick sort. So we'll pick the medianth, which is what it is here, but we'll round up to there. And we'll write down, scanning the list, let's write down the numbers that are bigger than 18. So 30, we'll write down, then 23, we'll write down, then 36, then 24, and then we'll write the 18. And then, again, scanning, we'll just write 12, 5, 2, 10, 15, all in order. That guarantees that 18 is now in the correct place, so I've underlined it. Now let's do the median of these 4, which we'll just again round up to make this, and the median of these 5, which is actually just this. From these 4, let's write them down. The ones that are bigger than 36 first, well, there aren't any, so 36 goes at the front, and then we just write down this one, and this one in the same order. And then likewise, write down the numbers in this section that are bigger than 2 first. That's 12, 5, 10, 15, and then we'll finally put the 2 at the end. That guarantees these 2 are in the right place now. Again, medianth, so let's take this one and this one here, I guess, just rounding up again from the middle. Put everything in order that's bigger than 23 in order from these 3, so that will be 30, then 24, then 23, so that sorts them. And then here, 12, 15, and then 10, and then 5. This must be in order since it's between 2 that are in order. And then this one here, we just need to circle this one and move it over. These 2 also just happen to be in order, but we'll swap these 2 to finish up, and we'll end up with our answer there. When first fit bin packing algorithm is applied to these, we get these numbers. Explain why n, so that's n is the size of the bin, it's how much you can put in each of these bins, must be either this or this. So let's think this through really carefully. We're going to take the 30, we're going to put it in. We're going to take the 12, we're going to put it in. That implies that n is bigger than 42, because 12 could fit in there. So that's fine. Then the 5 can't go in here. So if the 5 could go in there, then we could have size 47, but we can't. So the size must be less than 47, since 5 went into here. Then we put the 23 in here, that's fine. Then we also put the 10 in here. 5 plus that's not actually very interesting, is it? Because that's 28 and then 38, so that's not very interesting. But the 18 couldn't go in there, which makes a lot of sense. The 18 actually went down here. Actually, no, the fact that the 18 went there is interesting, isn't it? Because that makes 20... oh, no, because the 2 came next, of course. Yeah, sorry, the 2 came next. So we put the 5 there. Then the 2 went in there. Now, the 2 going in there means 30 plus, that is 42, plus 2 is 44. So n is bigger than 44 or 44. So it's bigger or equal to 44 since the 2 went there. Then the 23 went there. Then the 18 went there. Then the 10 went there. Then the 15 went there. That's all very interesting. But if it was 46, the 18 could have fitted into here, I think. Because that plus that is 28, plus that is 46. So it can't be 46, otherwise the 18 would have gone there. And it didn't. So it's got to be bigger than or equal to 44, but can't be 46. That just leaves 44 and 45. So just a bit of thinking through to do that. I would just recommend in a question like that, just doing the algorithm yourself. And that's essentially what I did, and you'll get it. Use first fit decreasing bin packing algorithm to determine it. Well, we have the numbers in decreasing order already. Remember, first fit decreasing is just the same as first fit. You just put them in decreasing order before you do it. But we have them in decreasing order, so that's great. So here are the bins. We put the 36 in bin 1. The 30 obviously can't go with it. The 24 can't go with either of those. The 23 can't go with any of those either. Now the 18, if we've got 44 or 45, I think the 18 can fit in with there. Because 18 plus 24 sounds to me like it's probably 42. Trying to desperately do some maths in my head very quickly. I think it's 42. So that can go in there, so that's cool. The 15, I think, therefore, can go with this one. Well, in fact, it can go all the way up here, can't it? Because if n is... we've decided now it's size 45. So it's not 44, it's size 45. So the 15 can go in here. The 12 can't go here still. But I think it can go all the way down here. Pretty easily. That makes 35, so it's 10 short, which is good because that means the 10 can go here. The 5, now 36 plus 5 is 41, so that's good. And then 41 plus 2 is 43, so that's good. And we only end up using 4 bins. So more efficient to do decreasing first fit sometimes than just first fit. And we'll have the answer. 6 is Dijkstra's algorithm. So we'll start at A and call that 1, and then it takes 0 to get to A since it's the starting point. That's our first point. We'll just label, using the working bars here, the distances from A to the various places you can go. So 32, 75, 16, 95. We'll label all those in. The shortest one of those is C, so we'll consider going to C next. We'll put that 2, take 16 to get to C. And then we'll find the distances from 16, because we already used 16 to get here, to all the places we can go from C. So 16 plus 50 is 66 apparently, 16 plus 70 is there, 16 plus 105 is there, 16 plus 113 is there. Now which of any of these, including the very first one we looked at up here, is smallest? Well, this one is. So let's label this one 3 and say it takes 32 to get here. And now let's do the same thing from here. So 32 plus 15 means it takes this long to get here, plus 33 is this. And that's all we can do actually from there. Again, smallest number in any of our working bars is this one, so we'll go here next, and that takes 47. And now let's do 47 plus 17. I hope you forgive me for just writing up there for a second. 47 plus that is 77. I think that's all we can go to. So the smallest one is the 64. So we'll go here next, and that's going around via this way, even though it seems ridiculous to do that, but we'll go around this way, and that takes 64 to do. 64 plus 50 gives us a new working box for this one, which is 114. The smallest thing in any of these is the 77. So we'll go there next, that takes 77. Let's do some more labeling here. So 77 plus 25 gets us a new distance here, plus 41 gets a new distance there. This is the shortest of all the boxes that we haven't already got numbers for, because we're only looking at these two now. So let's go this one next, that takes 102. And then finally, add 10 to 102 to get 112, which is the shortest way of getting here. So that would be the last box with 112. And our route was this, this. So A, B, E, F, G, H. And the shortest path was 1, 112 using Dijkstra's algorithm. Good. The algorithm has order n squared, but that's n squared for each node you use. And they want to use this algorithm on n different nodes. So actually, it's going to have order n squared times n, since you're applying it to n nodes. So that implies order n cubed. Now, we're going to do 200 nodes divided by 10, so that's an increase of 20 times the number. So we're going to do this amount of time times 20 cubed to find how much time it actually takes. Explain why this is approximation. So if you've got a thing that's order cube, that could be something like n cubed plus 2n. And the 2n will also increase the time a little bit. It'll just do it at much less order than the n cubed will, because of course n cubed gets bigger much, much faster. But it will apply some change to the amount of time. It will increase it by a small amount. But of course, because we don't know that, we were just told vaguely about this n squared thing. We can't really know for sure how much that adds. So it's just order of magnitude less. But it will increase it a little bit. Question number 7 then is about this stuff here. Again, can't remember the topic name. We've got partially completed activity network, and this is the precedence table here. So A, B, and C clearly don't need anything, so that's fine. D needs A to happen, and so does F. They both need A to happen, and so does E actually. Coming down here also needs A to happen. F requires here. I already said F requires A to happen. G requires B and F to happen. It also requires A, but we don't need to consider that since we already wrote down that in the F bit. So that's implied already. And then H also requires C, clearly, but also F and B from there. So it requires all of those. Good, and then the rest of the precedence table is here, and it wants us to go backwards now and fill this back in. So I requires D, E, G, and H. So that's going to require a dummy activity going down here to make that work. So I can now require all 4 of those. But then, and J also requires all of those. Then I got to K, and K only requires E, G, and H. So I realized I actually had to change this a little bit. So it's always good to do this with a pencil. But if you start I and J from there and have the dummy variable activity going this way, then you can get K going from here, and you can say it just requires E, G, and H. Now I've joined K and J up because I can see that some more activities require both of those. So let's join those up and say, okay, L requires all 3. So let's put in another dummy activity here to get to L, and then M and M don't require I. so they can just come out of j and k. Now the problem is they can't both come out of j and k because they need to all end at the same point. So I can make m go out of there to the end point, but n I'll just need to include another dummy downwards like this, and then I can go up to there. And I think that's an acceptable picture. At least I hope it is. It's slightly different to what the Marx team did. All activities take the same amount of time. Explain why D can't be critical. So there's a very logical way to think this through, but like the critical path here, if all the activities take the same amount of time, will be the longest path. And you can find paths of 5, right? A, F, G, K, M is a path of 5 activities. Now D, no matter how you go through D, like A, D, J, M, you're only using 4 actual activities, sorry. So D can't be critical because it's part of paths that are only 4 activities long, and since all the activities are the same length, it's going to be any of the paths that are 5 activities long that are actually going to be critical. So D can't be a critical activity because it's not part of a critical task. A critical path. Okay, cool. So our last problem is about simplex, I guess. So it's quite a long question, but we get lots of marks just for doing not much at all. So we're going to maximize time spent cycling and running. So they've given us the variables, which is nice. Train for most 39 hours. That means that x plus y plus z is less than or equal to 39. Spend 40% of time swimming. This is the hardest one to get, I guess. So 0.4 times all of our activities has got to be less than or equal to the amount of time spent swimming. So 0.4 of the amount of time she spends doing everything, 40% of the amount of time she spends doing everything has got to be less than or equal to the amount of time she spends swimming. So that's the hardest one, I think, to come up with on your own, but I don't think it's too bad. Spend a total of at least 28 hours swimming and running, so that just means, of course, x plus z is greater or equal to 28. Of course, you can fix this one up slightly. This is 2/5, so you times by 5 and 2, and then take away the 5x, and you get this. Now, this is greater than or equal to, so we're going to have to use what are they even called? The A ones. It says actually artificials, there it is, the A ones. Artificials, couldn't think of the word. So you're going to have to use slacks and artificials, obviously. So that's, sorry, we're asked to maximize cycling and running, so max y plus z. Okay, cool. So that's actually 5 marks for doing that. Now we're going to use some slack variables to make these into equality signs. So slack variable here, slack variable in there, we'll call it S1 and S2. Here's a greater than, so we're going to take away a slack variable and then add in an artificial variable. Just memorize that system is how that works, I guess. And now also we need to set up this I thing, which is minus whatever artificial variables you have. Minus A1, if you just put that on the other side, is just going to be this. And now I think we can get our tableau, and saying the word tableau is definitely the most fun thing in decision 1. But here's our tableau. We'll start here with just the 3 adding extras in these 3 things. That's genuinely how I remember that. So S1, S2, A1 are the 3 ones being added in, so I'll put those there. And then, okay, so now we just need to fill in this table. So first row is just 1, 1, 1, 1, 0, 0, 0, 39. Just reading from the coefficients. Next row is minus 3, 2, 2. There's no S1s, but there is an S2, and then none of these, and then 0. And then 1, 1, 0, 0, minus 1, 1, 28 will be there. P, this you want to think of as the equals sign. So actually I should probably just move these over, so P minus Z minus Y equals 0. So we're going to have 0, minus 1, and then all zeros and down to 0. And then finally I is, again, think of, move all these to the same side as I, and then the equals sign is equals minus 28. So it's going to be minus 1, no Y's, minus 1 Z's plus S3. And we'll have equals minus 28. So that's the initial tableau. I think that's all that's all I have to do. And then to finish off the question, it says they've done some simplex stuff, iterations, and they've got to here, or they've done one of them apparently, or whatever. They just want us to do another one. We have to choose the pivot first. So we choose this here because it's negative, and then we find the theta values by doing these divided by all of these. Now 11 divided by 0 we'll just say is infinity, I guess. I don't know, it's not, but it's bigger than 62 divided by 5, which is all that matters. Or maybe it is, maybe, who cares. We just ignore this. And then 28 divided by 1 is 28. This is the smallest one, so we'll choose this one here. So that's our pivot there. So what we'll do when we get to starting from tableau T, do another stage of simplex, You must give reasons, I guess. Choose that because it's what I said out loud. Choose this because it's -1. It's the only negative left. And then we do the thetas, choose the smallest from there. We get this, good. And then do another iteration of simplex. We know we're starting here with this 5 here. So okay, let's do this entire column divided by 5, and we get this. We can now replace this with a z because we've now solved for z there. So replace that with a z. Divide all the rest of this by 5, just say that's what I've done. And now what we want to do is we just want to get rid of any of the z's in here. We want to get a 0, 1, 0 essentially. Now this is already 0, so we can just leave it alone. I probably should have written here that this is just R1, but I forgot. Anyway, this one here has a z in it. I don't want it to. So let's do this entire row minus what I just made, this whole row here. So let's do that minus that. 1 minus 0 is 0 is 1. 0 minus 0 is 0. 1 minus this 1 is 0. This minus 0.4 is 0.4. This minus 0.2 is minus 0.2, and so on. Minus 1 minus minus 1 is 0. Yeah, that sounds good to me. And this minus 12.4 is this. And then here, again, what I want to do is just get rid of this minus. So if I just do this plus this row, this minus 1 plus 1, I'll get a 0 here. So let's just do this row plus this row. 0 plus 0, 0 plus 0, minus 1 plus this 1 here. 1 plus minus 0.4 is 0.6. 0 plus 0.2 is 0.2. 1 plus minus 1 is 0. And then 11 plus 12.4 is 23.4. And these are all positives now, so that's the end of simplex method. We'll have our answer, which is using, and just be careful because these are not in x, y, z order anymore. So we have y is 11, z is this, x is this. Just go back to the question to make sure you know which ones were x, y, and z, but they were apparently this, because I did look. And that's the whole of the session paper, so thank you for watching, and yeah.